So now starting with section 1.1, our first section of analysis, we should begin investigating the whole sequences in detail. And we're going to do that in this chapter because, well, a thorough understanding of sequences is pretty central in understanding the rest of, well, this book, this series, this Intro to Analysis class. So if you see here the two pictures, we have one sequence and two sequence. We're going to define what sequences really are. And then we're going to see some properties that they have, like convergence or divergence, as you can see from the title here. So the first things first is defining what a sequence is. And the sequence here, before I even define what a sequence is, this box in green means it's a definition. So if you see a green box, it's because there's a definition there. And this definition is sequence, right? So a sequence is a function whose domain is a set of positive integers. Sequence, as you have probably seen before, we usually write them as either an or in this little format. Again, it's a function with domain of positive integers, but yeah, a lot of the time we just write it like that, or as you can see here. And if you remember from high school, we can come up with pretty much any sequence we want. In this case, we have the sequence 1 over n. It's our first example. And here you see a purple box. Purple corresponds to examples. So if you see a purple box, it's probably an example. And our first example being 1 to the n. Here our domain isn't shown, but it's 1, 2, 3, 4, 5, so on and so forth. And then our output is 1, 1/2, 1/3, 1/4, so on and so forth. And you can see that this is described by the 1 over n here. So that's a sequence. It doesn't have to be explicitly, shown, like the 1 over n. We can simply write p sub n for a sequence, right, without having to write a formula. And this one gives us prime numbers. That's why we have a p. This sequence is the prime numbers. And again, the domain is 1, 2, 3, 4, 5, 6, so on and so forth. But that sequence gives us the prime numbers. Next is a sequence that looks a bit intimidating at first, but then once you start noticing it, it just oscillates between 0, 1, 0, 1, 0, 1. So these are examples of sequences. And from now on, all sequences will be sequences of real numbers unless I specify otherwise. This kind of allows us to dispense with unnecessary language. But we'll still allow other sequences, other types of sequences when needed. So if we take a look at these two sequences, the first example and the third example, we're going to call them a sub n and b sub n. These sequences, if we graph them, look something like this. Now, notice this first sequence. I'm going to just connect it with a green line here. Notice that by going out far enough, so to speak, in the sequence, that is like choosing n, this n right here, to be sufficiently large, we get closer and closer to 0, right? We get very close to 0. Similarly, in this sequence over here, b sub n, sure, if I connect the dots, it looks something like this. But this one, there are a bunch of points that are at 0, right? So it's not just very close to 0, they're at 0. But then if we go far out enough, we'll still be at 0, but then some will still be at 1. Right? So if we decide to measure closeness, right? Say our goal is to be 0.025 within 0? Well, it's clear that all the terms of the first sequence will be within that goal after a certain point. So let's take a look at our 39th term of the a sub n sequence. It's 0.0256, so it's still not within our goal, but it's getting closer and closer to 0. After that, we have a sub 40. Now that's exactly at our goal. We're 0.025 within 0. And then after that, every single point is within 0.025 of 0, right? From here on out, I should use a darker color. From here on out, right, 43, 43rd term, 44th term, so on and so forth, will be within our goal. We just had to go out far enough, right? So choose n large enough, little n. But these over here, the sequence b sub n, the 1 million in first term is 0. So that's definitely within our goal because it's at 0. But then the next term is at 1. And well, that's not close to 0 at all. Right, so this kind of gives us intuition as to how we're going to define what converges means. So we move on to the definition of convergence. So convergence, a sequence a sub n converges to a real number a if and only if for each epsilon greater than 0, there's a positive integer big N such that for all little n greater than or equal to big N, we have that the difference or the absolute value of the difference between the sequence and its limit point here, the number we're saying it converges to, is less than epsilon. Now this definition, I don't know of anyone who just read it for the first time and automatically knew what it meant. There's a lot to unpack here. The first thing I should mention is that this n here, the big N, I should write it over here. N depends entirely on epsilon. And you may not know what that means just yet, but our definition says that for each epsilon, there is a positive integer n. So given an epsilon, we can find that positive integer n, or big N, such that the rest of the definition follows. Right, so an example. For example, one sequence 1 over n, well, we think it converges to 0, right? It gets closer and closer to 0. So if it's getting closer and closer to 0, that means this is our sequence, a sub n, and 0 is our a here, right? Well, then I'm just going to write the rest of the definition. Then little n greater than or equal to big N, such that difference between our sequence, 1 over n minus 0, right, which I write over here, should be less than epsilon. That's what our definition says. But again, what does this mean? That means that given any epsilon, we can find this n here to make this come true. This to be less than epsilon. Less than epsilon. Right, so again, it may be a bit hard to see what I'm trying to say. So let's do this with an example here. And I'm going to draw the picture here just to make things even easier. So for example, if they gave us epsilon equal to 0.025, which I got from our goal, right? That was our goal for the last slide, to be within epsilon of 0. We are given epsilon to be 0.025. Okay, so that means, as we had said last slide, that for every n, or for every, right, after you get to the 41st term and afterwards, they're all within our goal, right? In the picture last time, they were all within our goal. And you can see it down here. Here's our goal. This line represents our goal. And 0 is down here. So we want our points to be within this area. And if you see, this is a 38th term. 30, sorry, you're right, 38. This is a 39th. 40 is exactly at 0.025. But then after 40, they're all within this area. Right? So if we're given this epsilon, any n after the 40th term gives us what we want to be within our goal. So then we use a sub n minus 0 because that's what our definition tells us, that this is a here because it's what we're thinking it's approaching. This is our sequence a sub n, and that equals 1 over n minus 0, which is just 1 over n, which we have here. And if n is greater than or equal to 41, well then 1 over n here is less than or equal to 1 over 41. And that is less than epsilon, or in this case 0.025. Right, so I'm just going to erase this because there's still something to come. So our big N here is 41. And again, the reason it's 41 is because at the term 41, the 41st term and after, they're all within our goal. But notice how this 41 depended entirely on this epsilon. Given that epsilon, now we know to choose big N as 41. So in essence, this just means given any epsilon, I can find an N here that from that point on, I am within my goal. I am within that epsilon of my limit point. Right? So then from here, we just say that N is 41. And, oh, sorry, a question came up here. So what if epsilon was 0.00025 instead of 0.025? Well, then we would still have to find that N such that every point after that, after a certain N, I don't know, just for the sake of example, I'm just going to say 50,000, that after that term, every single point is within this epsilon of 0, right? And this point right here, this epsilon, is down here. I drew the line. It's extremely close to 0. But because this sequence gets arbitrarily close to 0, we can still find that big N, right? This will keep going. Let's say this sequence keeps going down. Probably not accurate, but for the sake of this example, it'll get closer and closer to 0. And now maybe like if this line kept going, maybe like after this point here, all of them are within epsilon of 0, of our limit point. That's what this definition means. But now how do we prove that a sequence converges using that definition? Well, I'm going to erase the green up here so that it doesn't get in the way. But we're going to start by choosing epsilon to be greater than 0, right? Because epsilon has to be greater than 0 by definition. Okay, so then we're going to let n be an integer larger than 1 over epsilon. This is where the clever part comes in. The reason we're letting n be an integer larger than epsilon is because we want, by definition, 1 over n to be less than epsilon. Why is that? Because if n is greater than or equal to n, well then this would be greater than or equal to 1 over little n, and it would be within epsilon of our limit point, less than epsilon. So big N here, we're going to let it be larger than 1 over epsilon, because if we rework this out, 1 over n less than epsilon, that implies that n is greater than 1 over epsilon. Right, so we let n be that integer. So if n, little n, is greater than bigger N, well then this fraction is less than this fraction, or the value is less than that value, and this one is less than epsilon, since again, this over here, 1 over n less than epsilon, implies that n, sorry, I said that backwards. This right here, big N, being greater than 1 over epsilon, implies this one up here, that 1 over n is less than epsilon. So this means that this sequence, with our limit point being 0, in this case a is a limit point, we find that this difference, the sequence minus its limit point, is the same thing as 1 over n minus 0, which is equal to 1 over n, is less than epsilon. That's what this means. And so then we can conclude, well, this sequence converges to 0. If you were to use 1 for a, 1 over n minus 1, that wouldn't work. And you can try that out. You won't find a way to make that less than epsilon. And why? Because, well, this sequence doesn't converge to 0, so it'll end up not working. It's nice just how formally convergence is defined here. One more thing to recall. You remember this from probably high school algebra or any other class in high school, that if a and b are real numbers and epsilon is greater than 0, then that absolute value, this difference in the absolute value, being less than epsilon, we can just rewrite that like this. Right? So this means, actually, let me see if I have a picture. Here it is. This means that if we're given any epsilon greater than 0, we can, I'm going to just name this a, as we had the example 1 over n, our a there was 0, our limit point. This means that the terms of the sequence are within a minus epsilon, because we're going to call this distance right here epsilon, and then epsilon. So then this is a plus epsilon. So this means, as you can see right here, that all the terms of the sequence are within these bounds, a minus epsilon right here, and a plus epsilon right there. That's true, except for a finite set of subscripts. And what does that mean? That basically means that, for example, here, when epsilon was equal to 0.025, here was 1, our sequence. I'm just going to remind you of the sequence: 1, 1/2, 1/3, 1/4, so on and so forth. This one here, this was our first point, and then it was like 1/2, which was somewhere here, say 1/3 right here, and then 1/4, so on and so forth. This tells us that after a certain point, all the points, the rest of the infinite points, will be within this. Actually, there shouldn't be any points on this side, but the rest of the points are going to be within this epsilon, because the sequence converges. So again, this is just saying all the let me erase here. All the terms of the sequence are within a plus epsilon, a minus epsilon, except for a finite number of them. That's what that's saying. And this takes us to something new, which is a neighborhood. Before I even read it, just the word neighborhood, you think of, well, the people maybe who live close to you, who have houses close to yours. And that's what it basically means here. The intuition's the same. So it says a set Q of real numbers is a neighborhood of a real number x if and only if Q contains an interval of positive length centered at x, that is, if and only if epsilon greater than 0, such that that interval is a subset of Q. Again, kind of a lot to unpack, but this one's a lot easier to understand. This one we can just pretty much visualize it like this. X is our center, and this is an epsilon neighborhood of X, meaning that interval, any points in this interval are in the neighborhood of X. That's all that means. If there's a point out here, that point is not in the neighborhood of X. It's not in the epsilon neighborhood of X. Maybe if we had a neighborhood like this big, then that point would be in the neighborhood of X. But in this case, we don't. And if you can probably imagine, X can have an infinite amount of neighborhoods. We can always create different epsilon distances to create a neighborhood. But that's all neighborhood is. So we have a new a theorem or a lemma. Lemmas or theorems are always in a darker blue, a dark blue. And I didn't mention it in the last slide, but the proofs are always in light blue. And we're going to see it here. So this lemma says a sequence converges to A if and only if each neighborhood of A contains all but a finite number of terms of the sequence. So it's pretty much what I said last slide, but we're gonna go through the proof in detail now. And now this one's saying, again, only if it converges does it contain all but a finite number of sequence inside its neighborhood. So again, proof is in lighter blue. And we begin with our assumption. So suppose our sequence AN converges to A, and let Q be a neighborhood of A. So in this case, X is A, we have A, and we just have its neighborhood here. Right, that's our neighborhood. So there's an epsilon greater than 0 such that we get this neighborhood. So all it's saying is, hey, let's suppose we have this neighborhood. Okay, an epsilon neighborhood around A. Well, since A of n converges to A and epsilon is greater than 0, by definition of convergence, there is a positive integer n such that after a certain point, the points start being within our goal, within epsilon, right? Because epsilon is now greater than this difference here. So now this is saying all our points after n, at or after n, are within our epsilon. So that means that after a certain point, all these points are in here. That just means after a certain point, we can very well have points out here. I'm just going to draw some points out here. But after a certain point, all of them are within this neighborhood because of the fact that it converges, right? That is given from the definition of convergence. Well, this just means, again, what I just said, that for n greater than big N, we have that the points are within our neighborhood, just what I drew up there. So the sequence here, all the points of the sequence are elements of that interval, except for a finite, right? So like I said, thus Q contains all terms of the sequence except for possibly some of the terms, right? And it can be these terms that are not in that interval. They may be, but that's not guaranteed. And that's okay. So therefore, Q contains all but a finite number of terms of the sequence. So we proved one side. But because it's an if and only if proof, we have to prove the other side. So now we're going to suppose, and actually let me erase here. We're going to suppose now that each neighborhood of A contains all but a finite number of terms of the sequence A sub n. Now what we're trying to get at is assuming this and proving that the sequence converges to A. So again, that's our assumption. So what does that tell us? That tells us that if we choose epsilon greater than 0, then the neighborhood A minus epsilon, A plus epsilon, so the epsilon neighborhood around our limit point A is a neighborhood that contains all but a finite number of terms of the sequence from the definition of convergence. Sorry. Um, I shouldn't have said that. Backtrack. So given this epsilon neighborhood around A, we know this contains all but a finite number of terms of the sequence. Right? That's all that's saying. But now it's saying, well, if it contains all but a finite, then there's obviously this set, which is finite, of positive integers, such that if one of these wasn't in, so if it's saying that if you were to find a point that is not in our epsilon neighborhood of A, not in Q, well then that point, that subscript, belongs to the set S, because these are the points, the finite set S are the points that are not within our epsilon neighborhood. Right? So we're going to let N be the maximum of these, of this set. So if we let big N be the maximum of S plus 1, that means it's going to be part of our sequence A sub N that is within our neighborhood, our epsilon neighborhood of A. Why? Because, well, the maximum of S here was the last one that wasn't, that was the last point that wasn't part of the epsilon neighborhood. But once we add 1 to it, we get to the point that begins to be in the neighborhood, in the epsilon neighborhood of our limit point. So it tells us here. So now if N is greater than or equal to N, big N, well then N can't be an S, right? Because of what we let N be, which is a max of S plus 1. So by definition, after that N, after this little n, we should be in the epsilon neighborhood, or Q, which is what we're saying here. That is, A sub N and on is within that epsilon neighborhood of A. And this statement, as we saw from the last slide, the yellow box, is equivalent to saying this right here. And what is that? That's saying that our difference between our sequence and our limit point is within our goal, within epsilon. Therefore, after that N, greater than or equal to big N, we're within our goal, so we converge. And again, this proof can really be, I suppose, not as obvious without a picture, but if you draw a picture, it can help a lot. And we have this picture up here. You can kind of digest it with pictures better. And we're lucky that we do have pictures for analysis on the real line. Even though it's not for everything, but it does help. So last thing, I have a question. Last thing for this slide is, can a sequence converge to two different real numbers? Say, for example, can a sequence converge to A and B? What if I had some interval two intervals, one interval centered at A, one limit point, and centered at the second, another interval centered at the second limit point B? Can a sequence converge to two of those? Well, if you can think about it if you want to pause it, but take a look at that lemma that we just proved. What does that tell us? So we're going to move on and kind of that, right? We need a, if you pause it and you came up with the conclusion that it can't converge to two different points, congratulations. If you thought it could, that's okay. We're going to see why that may not be possible, or that isn't possible. So our theorem says if A of sub n converges to A and also to B, then they have to be the same limit point. They can't be the same one. So I have a picture again of the real line with our limit point A and our limit point B to help us with the proof, understand it. This one's a bit shorter. This is in, we start with our assumption, assume that A sub n converges to A and also to B, and that they're not the same limit point, so as we show in the picture. And just for the sake of argument, this proof, we can assume that A is less than B. This proof also works if you assume that B is less than A, but we just have to choose one of those. So we're going to choose that A is less than B. Well, we're going to set epsilon, and this is a bit of a clever part. We're going to set epsilon to be half the distance between B minus A. That means that this is halfway. So we're going to set epsilon equal to this right here. This is epsilon, and this is epsilon. Even though I know the B neighborhood might seem a bit bigger, I guess I didn't draw it right in the middle, but that's what we're setting epsilon to. Half the distance between B minus A. And we'll see why. Well, since A sub n converges to A, there's an n such that all the points after that n are going to be within this epsilon neighborhood of A. So after a certain point, the rest of the infinite number of points of the sequence will be within this epsilon neighborhood of A, of this A. After a certain n. So if you can already see where this is going, that means that there are a finite number outside of that epsilon neighborhood of A. Right? So this right here, before you go on, this is, let me erase a bit here. This here is A plus epsilon, since it's an epsilon neighborhood of A, and this is A minus epsilon. Well, this A plus epsilon, we can rewrite this by plugging in epsilon from over here. So now it's A plus half the distance between B minus A. A little algebra gives us that it's equal to this. Again, little algebra tells us it's equal to this. And go ahead and pause it to check it up if you want. But it'll equal B minus epsilon, which is where our other neighborhood ended. It's also B minus epsilon. Right? So why are we saying that? Well, because as we said, after a certain n, after a certain point, the sequence, all the terms of the sequence were less than this point, right? Because they're inside this neighborhood over here. So there are infinitely many terms of the sequence outside of this neighborhood over here, which I'm going to circle in red. There are infinite number of points outside of this one. And that contradicts our lemma from the last slide. So therefore, the sequence can't converge to B. So what conclusion can we come up with? Well, that we can't converge to both A and B if they are different. Right? They have to be the same limit points if it will converge to two different ones, which essentially is just saying it can't converge to two and it just converges to one limit point. We're just almost done with this slide. We're just going to come up with, define some things. But before we do, let's consider the sequence of natural numbers. Right, so it just goes 1, 2, 1, 2, so on and so forth. And it just keeps going on and on and on forever. And you can probably tell that this sequence won't converge because, well, it just keeps going on forever and there's really no bound to it. Which kind of gets us into our next definition. That a sequence, we say sequence A sub n is bounded from above if and only if there's a real number m such that all the terms of the sequence a sub n are less than or equal to that m for all n, meaning all the points have to be less than that m. So bounded from above, your intuition's probably telling you the right thing. It's that there's a real number m and no point is above that. Same idea with bounded from below. It's if and only if there's a real number p such that all the points of the sequence are greater than or equal to that p. And lastly, a sequence is bounded if both of the definitions above hold. So if it's both bounded from above and bounded from below. So now if you see down here, we have a sequence that is converging to or converges to A. Right? And remember from our lemma that we said, say we're going to choose epsilon equal to 1. So here is our neighborhood, our epsilon neighborhood, or A minus 1, A plus 1. Remember that infinite number of points are within this epsilon neighborhood, as our lemma told us and as we've seen. And there are only a finite number of points outside, right? In this case, I'm just going to draw 6. Well, because they're finite, we can draw parentheses, or I guess another open interval, around those points. And now we kind of like close all the points within that interval. And if we have all the points within an interval, that tells us, well, hey, this is bounded. We can bound every convergence sequence. So it leads us to our last. And before we move on, we just want to note, and I may not have said this before, but yellow boxes is something we're going to note, or a remark, something to keep in mind. So it says a sequence A sub n is bounded if and only if there are real numbers, p and m, such that all the terms of the sequence are within those numbers, are within that interval, as you can see, that closed interval, for all points, for all n, so all the points. And that's a different way of saying if and only if there's a real number s, such that the absolute value of the sequence of the points are less than or equal to that s for all n. So we move on with the theorem. So again, remembering from that picture from the last slide, I said it a bit quickly, but because we're going to go over it here. So if the sequence converges to A, then that sequence A sub n is bounded. And again, a picture to help us understand. So let's suppose A sub n converges to A, right? And as I did last time, we're going to choose epsilon to be equal to 1. We don't have to choose 1, but in this case, the proof works nicely with 1. So here's my neighborhood, my epsilon neighborhood, 8 plus 1. So there's a positive integer n such that every point after that n is within our neighborhood. So after a certain point, all the points lie within this neighborhood of A. Right, so there's only a finite number of points outside. I'm going to draw the points outside with a purple. And now we're going to choose S to be the minimum of all these points that are outside our interval, and A minus 1, which is the least point of this neighborhood. And then we're also including these because these are the ones outside. So the minimum one, the lowest. The lowest in this case is this one I'm going to circle in green. Right, this is the lowest. So that is what we set as S. Now the maximum, M, we're going to set to the maximum of the ones outside of the interval, and we're going to consider a plus 1 as well, which is some point here. And the maximum of those, well, is this one over here, right? That's the biggest value. So this is what we're going to set as m. Well, guess what? If we set an interval there, then all the points of the sequence lie within that interval. If you want to ask yourself why we include this a minus m and this a minus 1 and a plus 1 in this set, that's because, say we didn't have points to the left of our interval, then our lowest point in this case, or not even our lowest point, but we know we have a bound of a minus 1 here, where I drew this arrow. That means that that bound would work. But because we had points outside, lower than that, well, then we got the lowest point to those. But that's why we consider a minus 1, and the same thing works, same concept, same idea with a plus 1. Anyway, getting back to that idea, we now can form an interval at S over here and at M over here. And now all the terms of the sequence are within S and M. Therefore, the sequence is bounded. Just be careful. The converse is not necessarily true. And what's the converse? Is that if a sequence is bounded, then the sequence converges. And that is not necessarily true. And if you want as an exercise, you can come up with an example of that to show that in fact that if a sequence is bounded, then it doesn't necessarily converge. Last things, and then we'll be done with this section, is a sequence A sub n is said to be convergent if there's a real number a such that that sequence converges to a. So it's convergent is just what you learned maybe from calculus, although we're talking about convergence of sequences, not of series. And it's divergent if it doesn't converge. And these pictures, just to peek to the next section, notice how we have this sequence, a sub n, that we know converges to 0, right? But what if we add a 1 to every single term of that sequence? It just kind of shifts all the points 1 unit up, right? It just shifted everything 1 up. Now this sequence will converge to 1. And you can prove that. It shouldn't be hard. It's basically the same as proving this sequence converges. But this is telling us something about the sequences. This tells us that, well, that convergence is more of an internal property of a sequence, and it doesn't really depend on what the limit happens to be. And I say that because that's the topic we're going to pursue next.